Welcome to the third lesson in Session 5 on factoring polynomials. Factoring is a division technique used with polynomials for purposes such as solving and simplifying. Essentially, it operates like the distributive property in reverse. The factoring process is a progression to guide you through factoring problems. And we always start with the greatest common factor. And the greatest common factor has to be the first step in every single factoring problem. Next, we want to look and identify how many terms there are. The number of terms in the polynomial helps us to identify which factoring technique we're going to use. If we have 4 terms, we're always factor by grouping. Now, if there's 3 terms, we have some choices to make. We have to analyze the trinomial and identify if it's a simple trinomial, a complex trinomial, or a perfect square trinomial. And if we have a binomial, it's either going to be a difference of squares or a sum or difference of cubes. We start with the greatest common factor. The greatest common factor is the largest expression that divides each term in a polynomial evenly. As we said previously, GCF has to be the first step in every single factoring problem. So here's a few examples. In the first example, we have 4x to the second plus 12x minus 8. We're going to factor out the 4 as the greatest common factor. Since not all terms have an x, we can't factor out the variable. So we factor out the 4, and we're left with x squared plus 3x minus 2. In the next example, we have 3x to the third minus 12x squared plus 15x. So we have 3, 12, and 15 are the integers. They're all divisible by 3 is the largest factor, and they all have an x. So we can take out 3x. So we factor out 3x, and we're left with x squared minus 4x plus 5. In the third example, we have 5v to the fifth plus 10v to the third. So 5 and 10 has a common factor of 5, and we can take out as many as v to the third. So we take out as many variables as the smallest exponent. So we factor out 5v to the third, we're left with v squared plus 2. And the last example here is a little bit different. As x times the quantity of x plus 3 minus 2 times the quantity of x plus 3. So the common factor in this case is actually the binomial x plus 3. So if we factor out x plus 3, what we're left with is x and a negative 2. So x minus 2 times the quantity of x plus 3 is the result. Next, we're going to learn to factor by grouping. And remember, factor by grouping is the only factoring technique we have when there are 4 terms. To factor by grouping, we break the polynomial down into smaller groups and look for the greatest common factor among those groups. We then look for a polynomial common factor. Here's a couple of examples. In the first one, we have 2ab minus 6ac plus 3b minus 9c. So you look at it, first thing we always want to look for is the greatest common factor. Between 2, 6, 3, 9, A's, B's, and C's, there is no common factor among all 4 of these terms that will allow us to simplify this 4-term polynomial. So the next thing we look to do is factor by grouping. So I'm going to take the first 2 terms and the last 2 terms, and we're going to group them together. We then look for a common factor among the groups. So 2ab minus 6ac, we can factor out the 2a. With 3b and negative 9c, we can factor out the 3. So doing so leaves us with 2a times the quantity of b minus 3c plus 3 times the quantity of b minus 3c. So now this is the second part where we look for the polynomial greatest common factor. Now notice both of these expressions carry b minus 3c. So we have 2a times b minus 3c and 3 times b minus 3c. So b minus 3c is actually the greatest common factor. So when we factor out the b minus 3c, we're left with 2a and a positive 3, and that gives us our answer. In the next example, we have p to the third plus 3p to the second minus 2p minus 6. Again, the same thing occurs. We do not have a greatest common factor among all 4 terms. I know that I'm working with 4 terms, and I understand that grouping is the only technique that I have available. So we group the first 2 terms with the last 2 terms, making sure that you tuck that negative sign in with the negative 2p. That negative sign has to follow along with the 2p. So now we identify the common factor in my first group, which is p to the second, and my common factor in the second group, which is negative 2. Factoring that out allows us to see that p plus 3 is a common polynomial factor that we have, and when we factor out the p plus 3, we're left with p squared minus 2 and p plus 3. Next, we're going to factor binomials. Binomials are factorable if they are in the pattern of a difference of squares or a sum or difference of cubes. But those are the only factoring techniques we have for binomials. A difference of squares is identified when two perfect squares are being subtracted, and it looks like this. Notice you have two perfect squares, one being x squared, the other being y squared, and they're being subtracted. Hence the name, a difference of squares. It's factored as x plus y times x minus y. So you take the square root of each term, and you have opposite signs in the binomial. X plus y times x minus y. A couple of examples. The first one we have x squared minus 16. So x squared is a perfect square, 16 is a perfect square, and they're being subtracted. So that factors to x plus 4 times x minus 4. In the next one, 9x to the second minus 25y to the second. 9x squared is a perfect square, whose square root is 3x. 25y to the second is a perfect square, whose square root is 5y, and they're being subtracted. So we have a difference of two squares, and it factors as 3x plus 5y, 3x minus 5y. As we move on, we'll study a sum and difference of cubes. And this is identified when two perfect cubes are being added or subtracted. So in the first one, we have a sum of cubes, x to the third plus y to the third. Now, it factors as x plus y times the quantity of x squared minus xy plus y to the second. So you have the perfect cube x and y, they're being added in a sum of cubes, and then the next three terms go square, product, square. The signs are always alternating. So you start with a plus sign, the next one's going to be a minus sign, and then a plus sign. Square, product, square. In a difference of two cubes, you have x minus y leading it off, and again you go square, product, square. But in this case you have positive signs in the trinomial. X to the second plus xy plus y to the second. So the first thing you want to do is identify the perfect cube of each of the terms. So here's our two examples. We have x to the third minus 27. X to the third is a perfect cube whose cube root is x. And 27 is a perfect cube whose root is 3. And they're being subtracted. So this follows a pattern of a difference of cubes. So when we factor it, we'll have x minus 3 leading off. And then we'll have x squared plus 3x plus 9. So the cube roots are x and 3, so we start them off, x minus 3, and then we have square, product, square. The square of the first term is x squared, the product of the two terms is 3x, and the square of the last term is 9. And pay attention to the signs. We're always going to use a single negative sign, whether it's a sum or a difference. In a difference of cubes, we drop the negative sign off right away, meaning the other two signs are going to be positive. In the next example, we have x to the third minus y to the third. So the perfect cube of the first term is going to be 2x, and the perfect cube of the second term is y. So we'll start off as 2x minus y, and then the square of the first term is 4x to the second. The product of the two terms is 2xy, and the square of the last term is y to the second. So we have 2x minus y times the quantity of 4x squared plus 2xy plus y to the second. So that's how we factor a difference of squares and a sum or difference of cubes. Next, we're going to do some trinomial factoring. There are three types of trinomials we're going to cover. First, simple trinomials. A simple trinomial has a leading coefficient of 1. There are complex trinomials, and complex trinomial has a leading coefficient of anything other than 1. And there's also perfect square trinomials. Perfect square trinomials follow the following pattern. You have a plus, sometimes minus, 2ab plus b to the second. So that middle term can be positive or sometimes it can be negative. It won't be both. It'll be one or the other. We use a guess and check method to repackage trinomials to express them as the product of binomials. So we're going to start with some simple trinomials. Factoring simple trinomials just requires us to identify two numbers that are going to add to the linear coefficient and multiply to the constant. So our example, x to the second plus 7x plus 12. We identify this as a simple trinomial because it has a leading coefficient of 1. So we're just looking for two numbers that add to the linear coefficient, which is 7, and multiply to the constant, which is 12. So what multiplies to 7 and adds to 12? In this case, 3 and 4 fit that requirement. So we end up with x plus 3 times x plus 4. And that's our answer. All right, now you give it a shot. X squared plus 9x minus 22. Again, we have a simple trinomial because we have a leading coefficient of 1. So what adds to 9 and multiplies to negative 22? In this case, that's positive 11 and negative 2. So the answer we have is the quantity of x plus 11 times the quantity of x minus 2. Next, we're going to factor some complex trinomials. Complex trinomials contain a leading coefficient other than 1, and this is going to increase the number of possible combinations. So for example, we've got 2x to the second plus 11x plus 14. So 2x, this 2 right here, the leading coefficient, the coefficient of the quadratic term, makes this a complex trinomial. So what we know is that we're trying to find, we know the first two terms in each binomial are going to multiply to 2x to the second. We also know the last two terms in each binomial have to multiply to 14. The signs indicate, since we have two positive signs here, that we're going to be looking for numbers that add to a positive and multiply to a positive. So we're going to be working with a couple of plus signs. So all of this information we can gather by analyzing the trinomial, understanding what multiplies to 2. 2 is a prime number, so that's very helpful. The signs always give us information about what our answer is going to look like. So in this case, what multiplies to 2x squared multiplies to 14, but also the trick is to find the right combination that adds to 11x in the linear term. And in this case, 2x plus 7 and x plus 2 fit that combination. So here's a few examples for you. Try out some different combinations of numbers to see. This is a guess and check method, but the more you get, the more experience you get, the more efficient you will be at factoring the trinomials. So the first one is 3x to the second plus x minus 10. Feel free to pause and then push play when you have an answer that you're ready to check. So the correct factored form of 3x squared plus x minus 10 is 3x minus 5 times the quantity of x plus 2. 4x squared minus 3x minus 1 has a correct factored form of 4x plus 1 times the quantity of x minus 1. And lastly, 6x to the second minus 19x plus 15 has a correct factored form of 3x minus 5 times 2x minus 3. As we move on, we're going to factor some perfect square trinomials. Perfect square trinomials are important to recognize because we're going to use them when we solve by completing the square, when we solve quadratics, and we also use them quite a bit when we're working with conic sections. So perfect square trinomials follow one of the following two patterns. It's either going to be a squared plus 2ab plus b squared or a squared minus 2ab plus b squared. Now we recognize the pattern by identifying the first and last terms are both perfect square. That should be what tips us off. If the first term is a perfect square and the third term is a perfect square, there's a really good chance we have a perfect square trinomial. The linear term always ends up being twice the product of the square roots of the first term and the third term. When factored, they can be expressed as the square of a binomial. For example, a squared plus 2ab plus b squared factors to the quantity of a plus b squared. And a squared minus 2ab plus b squared factors to a minus b quantity squared. Here's a few examples. We have x squared plus 7x plus 49. So notice we have a perfect square leading off is x squared. We have a perfect square at the end in positive 49. And the middle term turns out to be double the product of those two squares. So we do have a perfect square trinomial. Turns out to be the quantity of x plus 7 quantity squared. The next one, x to the second minus 20xy plus 100y to the second, factors to quantity of x minus 10y squared. And lastly, we have 3x squared plus 24x plus 16, and it factors to 3x plus 4 quantity squared. That wraps up our lesson for factoring. And to understand it was kind of long, I encourage you to take your time with those examples, push pause, answer them as best you can, go through and study. Feel free to email us if you have any questions. And as always, we got to successfully complete the quiz in order to earn credit for completing this lesson. Good luck.